What is TrueQuant? Eroa TrueQuant IQQ is a measurement system that provides a complete and verifiable compound identification system, the I in IQQ. A complete daily, fully detailed QA/QC on instrument performance, including source and injector, the first Q in IQQ. A measurement system that removes systemic variances from raw data for better quantitation, the second Q in IQQ. This includes a system to correct for ion suppression and other source variances, and B, a complete and universal normalization system for sample-to-sample normalization. The Eroa IQQ leverages the best approaches of two Eroa aspects, the Eroa phenotypic protocol and the Eroa basic protocol. It uses a well-defined biochemically complex long-term reference standard, the Eroa LTRS, and a chemically identical but isotopically different internal standard, the Eroa IS. The TrueQuant workflow leverages the best aspects of two Eroa protocols, the phenotypic protocol and the Eroa basic protocol. It uses a well-defined and biochemically complex long-term reference standard, the Eroa LTRS, and a chemically identical but isotopically different internal standard, the Eroa IS. These two standards, the Eroa LTRS and the Eroa IS, have been carefully calibrated to one another. That is, they are chemically identical but are isotopically distinct and are present at the same concentrations in all samples. They serve different purposes at different points in the workflow. The Eroa LTRS is a complex standard containing hundreds of compounds labeled at both 5% C13 and 95% C13, both being present at equal concentrations. It consists of most primary and intermediary metabolites. This sample is a long-term reference standard in that it is prepared to always provide the same concentrations at the same concentrations present. While it is chemically complex, it has a fixed number of compounds that will always be found. Noise artifacts will be easily discriminated and thus may be removed from the data set. For at least the next 10 years, it will always be the same. The LTRS provides a complete QA/QC for instrument performance. As a defined but chemically complex isotopic material, when the instrument falters in the middle of a run, you will see this change, as well as a method to correct, if possible. To be most effective, there should be multiple injections of the Eroa LTRS over the duration of the analysis, for instance, at the start and end of the run and approximately every 10th injection during the run. The Eroa LTRS is also used for verified compound identification. Based on their Eroa chemical characteristics, LTRS metabolites plus their fragments and adducts can be readily identified, and a library of retention time, M/Z formula physical characteristics is generated to measure the same hundreds of compounds in any experimental sample. The Eroa IS is chemically identical to the Eroa LTRS, but has only the 95% material. It is put into every experimental sample at a concentration equal to that of the LTRS. As an internal standard that is present in every sample, the quantitation of natural abundance analytes is made relative to the internal standard, and its ion suppression may be corrected. As we will show later, using the suppression-corrected concentration improves sample-to-sample normalization dramatically. As we say, Eroa makes better metabolomics easy. These data are significantly better than raw data. This is a schematic of the Eroa TrueQuant workflow. At the outset, there are three different samples to keep in mind. The first sample type is the experimental sample, A, shown here. Those samples which we are seeking to analyze. Isotopically, they are natural abundance. At the start of the experiment, they should be extracted and dried under nitrogen so that they have all of their chemical concentration present at 0 volume. They will have an isotopic signature as shown in image A'. The second sample type is the Aroa IS-B. When a standard aliquot of Aroa IS is used to resolvate the dried experimental samples with equal amounts of the internal standard to make samples, which will be analyzed. The Aroa IS has an isotopic signal like that shown in image B'. So once combined with the natural abundance experimental sample, we expect to see the isotopic signature shown in C' in these analytical samples. The third sample type is the Aroa LTRS. This is a basic Aroa sample that contains both the Aroa C12 5% and the Aroa C13 95% halves, at the same concentration as in the analytical samples. As expected, it will show the isotopic signatures like those in image D'. Since we do not need to quantify the components of the Aroa LTRS, we can use the LTRS samples to examine and verify the identity of every peak. We always get the correct formula for an Aroa MS peak, image D'. However, most molecular formulas represent more than one compound, and these isobaric compounds cannot be distinguished. We always get the correct formula from an Aroa MS peak, see image D'. However, most molecular formulas represent more than one compound, and these isobaric compounds cannot be distinguished by MS alone. Therefore, a secondary identification system, such as ion mobility, image D1', or fragmentation, see images D2 or D3', may be used to identify which among the formula's isobaric compounds the peak represents. More on this in the next few slides. In summary, there are two sample types, the Aroa LTRS and the Aroa IS. The analytical samples contain the Aroa IS, so we may quantitatively analyze these samples, correct compound peak areas for suppression, and normalize the samples to one another while applying the identities we determined using the deep qualitative analysis of the Aroa LTRS. As discussed above, the compound identities are determined on the Aroa LTRS and transferred to the retention-aligned peaks in the analytical sample. This frees the analytical samples to be completely devoted to quantitation. As we have seen, the formula is always acquired from the Aroa basic peak, image D'. Because its detection and character are so secure, being triply redundant, this formula will always be correct. However, a formula does not usually identify a compound, but rather a collection of isobaric compounds. To determine which of the isobaric compounds a given peak represents, a secondary analysis, such as ion mobility, shown here in D1', or MS-MS fragmentation, images D2, D3, and D4', are usually required. Aroa's cluster finder software gathers the information associated with every peak as Aroa fragments D2', and we can exclude fragmentation noise and determine the formula of the fragment and associate it with its parent, D4. As of version 4, we will support ion mobility completely. Note that in both cases, the Aroa patterns are seen free of noise which is unlike normal spectroscopy where the noise cannot be removed. And in the case of MSMS, we actually do get a formula for every fragment. QA/QC is determined by the AROA LTRS. While the mixture is chemically complex, the ability to remove noise means that every AROA LTRS injection will have between 500 and 1500 peaks, depending on the instrumental performance on any given day. If the same AROA LTRS sample is injected multiple times during every analytical run, the response on any given instrument for any given protocol will become known. Therefore, A. During every analysis, the AROA LTRS should be the first and last injections, and approximately every 10th injection while running. This will make it apparent if the system degrades or is degraded in any way during the run. B. The AROA LTRS provides the following measures of instrument performance. The number of AROA peaks seen is a measure of instrument sensitivity. The retention time for selected compounds is a good measure of chromatographic conditions. The ratio of an in-source parent to their child fragment is a good measure of source conditions. The total signal for all AROA peaks is a good measure of injection accuracy. Quantitation in every analytical sample is based on the internal standard for many compounds. To understand the AROA approach to quantitation, ion suppression, correction, and normalization, we need to consider an experiment in which multiple different-sized aliquots of a single analytical sample are dried and resolvated in a constant volume of AROA IS. In such an experiment, we know that the natural abundant compounds will all track linearly with their original aliquot size. Therefore, the expected concentration of all natural abundance compounds in all analytical samples will be similar to that shown on the figure on the left. Since the amount of internal standard in all analytical samples is the same, the expected concentration for each compound in the AROA IS is expected to correspond to the figure on the right. In this slide, what we expect to see in the MS responses from the natural abundance and AROA IS respectively is seen in figure A and B at the top of this slide. In blue, we see the actual raw data for the analysis of these samples. In figure C, blue dots, the natural abundance MS responses can be seen to be severely inhibited for the higher concentration samples. And we see that the raw data for the internal standard shows the same problem in figure D. The higher concentrations are showing significant degradation. We can see that this signal inhibition is equally inhibiting to both the natural abundance and the internal standard sides. Furthermore, when we look at the ratio of the natural abundance to internal standard, as shown in figure E, we see that there is no inhibition. The ratio is correct as plotted, perfectly correct. Because this effect is concentration dependent, it represents ion suppression. Knowing that the internal standard is constant and their ratio is not affected by the suppression, we can correct all of the raw data signals for suppression, and these corrected values are seen in images C and D using the red dots. Pretty clearly, these red dots in graphs C and D correspond to the expected graphs in A and B. It turns out that correcting for ion suppression is actually pretty easy. The aliquot samples in this experiment were completely within the normal range of metabolomic samples. That is, they were not larger than most samples we would normally have run, and yet suppression was much more common than expected in our most concentrated samples. No compounds showed no suppression, and the average level of suppression was approximately 40%, with 50% of all compounds being suppressed between 20 and 60%, as shown in the graph on the left. The most severely ion-suppressed compound we saw was suppressed at 91.8%, shown on the right, and when its raw data was examined, the raw MS was actually negatively correlated to the actual concentration. That is, it shows less signal the more compound is injected. In general, compounds suppressed less than 60% in these samples were at least positively correlated with their actual concentration, although the correlation may have been poor. Those compounds that were suppressed between 60 and 80% were simply not correlated. Injecting more compound did not result in a larger peak. And those compounds suppressed more than 80% showed a negative correlation, as shown here. The more compound injected, the lower the signal seen. Using suppression-corrected data, it was possible to use a dual Mustis normalization to normalize all of the samples, even though they were extremely different in their original aliquot sizes. This summary slide shows that the raw C12 data in black exhibiting severe ion suppression. The suppression-corrected data is shown in green, and the C12 normalized and suppression-corrected data is shown in red. While these samples were very different sizes, they were perfectly normalized and mathematically corrected to report signals as if all the samples had started at exactly the same size. This technique will remove the concentration variances due to the different concentrations in urine, different biopsy sizes, and/or other sample phenotypic variances. While ion suppression is a function of molecular structure and therefore different for every compound, the normalization factor computed from the suppression-corrected data is common to all of the compounds in a sample. Therefore, the normalization correction factor may be applied to every compound, even if it is not associated with an internal standard and is therefore not suppression corrected. In other words, those compounds for which no standard was seen may be normalized, and they normalize quite well. They may not be suppression corrected, but they may be normalized. Thank you. We would be happy to take any questions. Would you like to try TrueQuant in your own laboratory? Would you like to reproduce this experiment? We would be happy to provide you with the material to do so, and get your feelings on it. Please write us at info@aroatech.com, and we will send you a free kit. Thank you very much.